This instructional video is designed to show you the effect of having distinguishable particles on your partition function. So the general idea is that we want the partition function of the entire system, and we're going to claim that we have three different types of particles that are acting as monatomic ideal gases. So we're going to need a full partition function for type A. We're going to need a full partition function for type B. And we're going to need a full partition function for particles of type C. Now, there are a couple things to think about here. The total number of particles in your system are going to be distributed between type A, type B, and type C. Now, for each individual particle type, the partition function will look pretty much identical. So, in that case, I'm just going to use the black marker to show that full partition for an individual is going to be the little q for that individual raised to the number of particles of that individual type divided by its factorial. So this format mimics completely what we already know when we have indistinguishable particles and we can't tell them apart. And so in this case, we can just replace the subscript I of type A, type B, or type C as needed. And in order to step through the remainder of the derivation, I'll show what that looks like for one when we're doing derivatives and such. But for the entire thing, I'll actually use the colors. So the little q, the individual, will be the same. Now the mass is going to be different for our different particle types, but they do all occupy the same amount of volume. And so the only thing left to do then is write out what that formula would be to find the pressure. So if we want the pressure, we take our factor kT and multiply by the partial derivative of the partition ln q with respect to volume, while holding number of particles and temperature constant. So we have a partition function. It's a little more involved because we have distinguishable particles. We have a formula that we can use, and so we can actually get out an answer. So the first thing we need to do is actually find ln of q total, since we want to find the total pressure of this system of three different ideal gas particles. So for ln of q total, that's going to decompose using our natural log rules. Ln of each part in a sum. So ln qa, ln qb, and the natural log of qc. So once we have all of that in place, then we can break that out further, and recognizing that for each of these individuals, this rule is in place. So for any individual, we're going to have the following breakdown. That's ln of the individual in factorial. So with this setup, we can now substitute in the little q sub I, and because this is a volume derivative, the only term that's actually going to survive taking the partial is going to be the ln of v. So what that means then is that the partial derivative in beta is going to look like the following. We'll have a sum in three parts. So we're going to have the number of particle type A divided by volume plus the number of particle type B divided by volume and the number of particle type C divided by volume. Now, since all of these particles are occupying the same space, these volume terms are all going to be identical because we have the partial of L and Q with respect to volume. In order to get the pressure, we just need to multiply this answer by KT. So at this point, we can write that our total pressure is going to be particle type A, KT over V, plus particle type B with the same KT over V, and particle type C plus times the same KT over V. Now at this point, we recognize that we can make a substitution. The number of particles times this Boltzmann constant gives us the number of moles times the gas constant. And so as a result, what we have is the following: that our total pressure is going to be the moles of A times RT over V plus the moles of B RT over V plus the moles of C RT over V. And so the thing that an observant chemistry student will recognize is that nRT over V is just a pressure, at which point we can make the final valuable conclusion that the total pressure is going to be equal to the pressure from gas A plus the pressure from gas B plus the pressure from gas C. And if that result looks familiar, it should. This is effectively a derivation from first principles of Dalton's law of partial pressures, where we have a partition function describing the entire system. We have a rule for determining the pressure when given a partition function. By stepping through and following all of the rules in our calculus, we're able to find that the total pressure of the system is equal to the sum of the individual pressures, the partial pressures of the gases that compose it.